So here I have a circuit for you. It's definitely not the most complicated one I've ever seen, but it's also not the simplest one either. So before we jump into solving this in the next video, I wanted to introduce you guys to Kirchhoff's rules. And like Ohm's law, Kirchhoff's rules are really helpful for when you're trying to solve for unknown quantities in a circuit. So let's jump right to it. The first rule is what I like to call Kirchhoff's junction rule. So what a junction basically is do you see this little part here where the wire splits into multiple parts and then comes back together again? Well, that's going to be the junction in our case. So what the junction rule basically says is that the sum of the currents flowing into a junction is equal to the sum of the currents flowing out. And that makes a lot of sense intuitively, because none of the current that's going into this junction should be lost or gained when it comes out of the junction. And so the junction rule relates really well to the concept of conservation of charge. Now the second rule is going to be Kirchhoff's loop rule. A loop in this case is basically a path that you can take through the circuit that gets you from one point and around and back again. So the first loop that I can see here is if we start at the battery and go through this wire and up through this resistor, back down, leaving the junction and around again, that would be our first loop. Our second loop would be pretty much the same thing, except you'd go through this resistor instead and around and back again. So the loop rule basically states that the voltages around one loop should sum to 0, which means that some of the voltages should be negative. So if we say that this had a positive voltage, then we can assign this a name of voltage 1, and this would be voltage 2, voltage 3, and voltage 4. So for the first loop, we could say that we're starting off with a positive voltage, voltage 1, and as we go through the circuit, we'll experience a voltage drop at this resistor. So we're going to drop our voltage at this resistor, or voltage 2, and when we get to this resistor, we'll experience another voltage drop, so we're subtracting the voltage value here, and that equals 0. Now for the second loop, it's pretty much the same thing, except we're going through this resistor now. So we're starting at the battery, we're subtracting the voltage at this point of the circuit, and we're subtracting another voltage drop at this point of the circuit, and that equals 0. You can think of the loop rule as also stating that the total voltage should equal the component voltages of the loop. So if you take these negative values and move them over to the other side, you'd get that voltage 1 is equal to positive voltage 2 plus positive voltage 4. So the voltage of this element and this element, when combined, should equal the total voltage. Same thing for the second loop. Voltage 1 is equal to voltage 3 plus voltage 4. Just like the junction rule related really well to the conservation of charge, the loop rule relates really well to conservation of energy. Because if we define the voltages like we did in these two equations here, and we end up with 0 at the end, that means we're neither gaining nor losing a potential difference. So hopefully now that you have a couple of more tools under your belt, we have Ohm's law, the junction rule, and the loop rule so far, we can try to solve this circuit in the next video given a couple of known values.